Here we're looking at part 2 of question B1, and we're looking at the unified atomic mass unit and the nuclear reaction. So this is topic 7. Now topic 7 has in the data booklet has just E is equal to mc squared as your one formula, but there is important information here in your data booklet. We have the electron rest mass, the proton rest mass, the neutron rest mass, and your unified atomic mass unit, your U, is given there. Now just a discussion here of the units. It's either given in kilograms or it's given in this mega EVC to the minus 2. Mega EVC to the minus 2. Now the mega, we know, is just a multiplier. A mega is 10 to the 6. It's a million. But this EVC to minus 2 is used as a mass unit because E is equal to mc squared. So when I put in for my mass, I put in this unit EVC to minus 2, and I multiply it by c squared. Those cancel out, and we're left with an EV, which is a energy term. EV is energy term. Remember, 1 EV is equal to 1.6 times 10 to the negative 19 joules. So you need to understand these units that you use. Okay, so let's go to the question then. Define the term unified atomic mass. Now this is defined as 1/12 of the mass of the carbon-12 isotope. That was where they got that from. You can't just give this number, you had to define what it was. It says the mass of a nucleus of Rutherfordium is 254. 254 is 2541001 U. Calculate the mass in giga EVC to minus 2. So we're going to have this 2541001 times this value over here, 931.5 mega EVC to the minus 2. Now when I do that on my calculator, I get this number over here, 2369.2432, and that would be mega EVC to the minus 2. But they want it in giga. Now remember, a giga is 10 to the 9, and a mega is equal to 10 to the 6. So 1 giga is equal to 1,000, 10 to the 3 mega. So if I want to convert this to giga, I've got to divide this by 1,000 or take 3 decimal places out. So I'm going to get 236.7 giga EVC to the minus 2. And it says in C, in 1919, Rutherford provided the first artificial nuclear transmutation by bombarding nitrogen with alpha particles. The reaction is represented by the following equation. Now, firstly, this word transmutation, this is the word that is given to the making of new elements by bombarding smaller ones with small particles. So your alpha, now you need to know what your alpha particle is. It's basically a helium nucleus. It's got 2 protons and 2 neutrons. Remember, this is how it works. You've got your protons and your neutrons. This is your total number of nucleons, total number of protons and neutrons, and the smaller number here, your atomic number, is your number of protons. So we need to identify X. So in doing this, we just need to, if I write it out over here again, I've got 24 plus in 714 goes to oxygen 817 plus X. What happens here is that you just look at your number of protons firstly. You've got 2 and 7 is 9, but here you've only got 8, so you must have 1 there. It's just a matter of balancing both sides. And here you've got the number of nucleons. You've got 18 on this side. You've only got 17, so you must have 1 there. So you've got this particle. Basically, it's just a proton. So because it's obviously got no neutrons, because the number of nucleons is the number of protons. It's also the hydrogen nucleus, H11 particle. Going over the page. It says here the following data are available for this reaction. Let me just rewrite the reaction here. So you've got your alpha plus your nitrogen goes to your oxygen plus your X. And you're given your masses here. And you're also told that the initial kinetic energy of the alpha particle is 7.68 mega eV. Determine the sum of the kinetic energies of the oxygen nucleus and your X particle. Assume that nitrogen nucleus is stationary. So basically we've got energy conservation. The energy before must equal the energy after. E before must equal the E after. But remember that your mass and your kinetic energy are all parts of that energy. So you need to combine both on either side. Now, when we look at this, if we look at our mass difference, if I take my 16.8383 and I subtract from this side, so that's 16.8383 is that. If I subtract the mass of that, which is 13.0942 plus 3.7428, if I subtract those two, they're all in giga eV, I get 0.0013 giga eVc to the minus 2. So that's the energy that I've got. If I that's the mass. If I put it in terms of energy, I therefore have, and I put it in mega, 1, 2, 3 will change it into mega. So I have got 1.3 mega eV. That would be the extra energy that I've got in terms of mass on the right hand side. But I've got this energy that came in on the left hand side with the alpha, the kinetic energy. So I've got 7.68 minus the 1.3, which gives me a 6.38 mega eV. That is the leftover energy, the extra energy, and that must be in terms of the kinetic energy of these two particles. Okay, so this is actually quite straightforward. I mean, it's just a matter of adding and subtracting and making sure that you understand your units and work with your multipliers. So the reaction in C produces oxygen O17. Other isotopes of oxygen include O19, which is radioactive with a half-life of 30 seconds. State what is meant by the term isotopes. So isotopes are elements, the same element. That means same number of protons or same atomic number, but a different number of neutrons. And I can just explain it using here. Here we've got your regular isotope for oxygen is this. That's the one that's most common. It's very stable. And then we had this O17 and this O819. Now, all three of these are oxygen. They all behave like oxygen, except in this case over here, your oxygen 19 isotope is unstable. It is radioactive, so the nucleus actually is not stable. It breaks apart. Now, what is different between these two? Well, this one has got 8 neutrons. This one has got 9 neutrons, and this one has got 11 neutrons. Okay, so the same element, but different number of neutrons are different isotopes. Now, let's just have a look at this. Define radioactive half-life. Now, the half-life, the radioactive half-life, is the time taken. So it's a time factor, the time taken for either two things, for the activity of a sample to halve, or the number of radioactive nuclei to decrease by half. Alright, so it can be viewed. I generally tend to like to view it in terms of activity. The activity, the number of disintegrations to go to a half, or the time taken for that to go to a half. Alright, going over the page here, it says a nucleus of isotope O19 decays to a stable nucleus of fluorine. The half-life of O19 is 30 seconds. At time t is equal to 0, the sample of O19 contains a large number N0 nuclei of O19. On the grid below, draw a graph to show the variation with time t, the number N of O19 nuclei remaining in the sample. And we should consider from time t is equal to 0 to 120. So you'd want to use all your scale here as much as it. Don't try and fit everything just in a bit of it over here. Use the whole thing. So it would go to, at the end here, 120. It's quite difficult for me to see it on the board here, but so here this would obviously be 60 seconds, this would be 30 seconds, and this would be 90 seconds. Now, because 30 seconds is a half-life, after 30 seconds, this N0 is going to be a half, so it would be somewhere over there. I'm not doing it exact, but this would be N over 2, and that would correspond to that point about over there. Then at 60 seconds, you would be half of that again. That would be N0 over 4. So you'd be somewhere over there. After 90 seconds, this would halve again, so it would be N0 over 8. Like that. And after 120 you'd be there in 0 over 16. So you'd have something like that, graph like that.